Hi everyone, welcome to this probability refresher for business analytics video series. My name is Teja, and in this video we're going to look at some extensions of the probability laws that we discussed in the previous videos. So in particular we're going to look at conditional probability. So what is conditional probability? It's the same as the probabilistic, same as the probability function, and except for one twist, which is that let's say you have two events. Um, let's say this is our sample space, and we have event A and event B. So this is A and this is B, and this is our sample space omega. Then we can ask the probability of event A given that B has already occurred, which means that so this is a question where we are saying that maybe there are a bunch of outcomes in B, bunch of elements in B that have already occurred. Let's say they have occurred, something has occurred in B, and the question is what is the probability that A has occurred. So A would occur if there's a common point between A and B, right? So that gives us an intuition about what would conditional probability be, and the notation for this is probability of A given B has occurred. So this is a way to denote conditional probability. Is nothing but the probability of elements in the intersection of these two events, which is A intersection B, divided by the probability of B itself. Okay, this is the definition of conditional probability. It turns out that with this definition, this renewed probability also satisfies the axioms that we discussed in the second video. So um, so for all intents and purposes, it's basically attacking on this additional symbol. But of course, you need to be cognizant that there is this conditional probability. So this is under the belief that something else has already happened. Okay, some outcome in B has happened. Okay, so there's a nice interpretation to this via what is called multiplication rule, which just means that if I have a so if you take the denominator to the left hand side, you can see that probability of A intersection B is nothing but probability of B times probability of A given B, right? So it's somehow that the this is the probability of common outcomes. So the belief that I ascribe to each of the outcomes, it's only about the outcomes in the intersection of these two events, and that probability is the same as the probability that you would assign to all the events, also all the elements in B times this conditional probability that we just, this is just by definition, so there's not much going on here. Um, so but the interesting extension to this is that if you think of three events, for example, let's say A1 intersection A2 intersection A3, then you can actually split this down into in multiple ways. For example, one way is this probability of A1 given probability of A2 intersection A3 given A1 times the probability of A2 given A1 times, oh sorry, this is yeah, this is fine. I just added one additional factor unnecessarily, so let me just change that. um, which is equal to probability of A1 times probability of A2 given A1 times probability of A3 given A2 and A1. Okay. So what did we do here? We first of all we thought of A2 and A3 as a single event. Let's call it B. Then we just applied the conditional probability definition here. So it says probability of A1 times the probability of B given A1. And then we just focus on this term with the given A1 tacked on to both both these terms, where now it's think of A2 intersection A3 as A2 and then A3 given A2 with A1 kept as it is. Okay, this is just an easy way to remember this. So this is called the multiplication rule. There's also a couple of nice extensions, and in fact, the second extension that I'm going to tell you is about Bayes' rule. So before that, let me just talk about quickly this law of total probability. Okay. So the total probability rule or the law of total probability, it just means that um, if I have a event um, A, so let's say this is event A, and let's say this is a sample space, and I'm always using this square to represent the sample space, but it can be, as we saw in previous videos, it can be just a few numbers, or it could be infinite number of elements or outcomes, and so on. But let's say this is the event A, and this event can actually be broken down somehow, and it's going to be as follows. So let's say I break the sample space into multiple events. So maybe my first event is going to be this. Okay, this is B1. My second event is going to be this, which is B2, which is just this bar over here. Maybe the third event is going to be B3. Maybe the fourth event is going to be B4, and the fifth event is going to be B5. Okay, and A is this actual, ellipsoidal looking thing in there, and this is the sample space. The law of total probability says that I can write probability of A in this way, which is I can write probability of A as probability of B1 times probability of A given B1 plus probability of B2 times probability of A given B2 plus, and a couple of more terms, plus probability of B5 times probability of A given B5. And why is this true? You can see this by just using again the definition of conditional probability, which is that the first term is just probability of A intersection B1 plus four terms, three terms in between, and then probability of A intersection B5. Okay, and you can see that probability of A intersection B1 is this region, probability of A intersection B5 is this region, and similarly A intersection B4 is this region, and probability of A intersection B3 is this region, and probability of A intersection B2 is this region. So it's essentially is equal to probability of A. Okay. So what was the interesting thing that I chose? If you can see that I chose the sets or events B in such a way that they are disjoint, and their union is equal to the sample space. Okay, so they're disjoint and they're mutually exclusive and exhaustive. That's all it means. So because I chose these other events in such a way, I can write probability of A as a huge summation of a bunch of conditional probabilities times probabilities of some events which are disjoint and span the which are disjoint and kind of completely cover the sample space. Okay, so this is the total probability rule. It is sometimes useful to do it when you can handle. So if you want to compute, as if you remember from one of the previous videos, probability, the use of probability as a tool is one of the tools is to have an event of interest, maybe event A, and then talk about how to compute or give a belief on this number A. Okay, so you may have beliefs on just the outcomes, which are the elements of the sample space, and then you may want to compute. You may have figured out an event of interest, maybe event A, and then you want to ascribe your belief to that event A. And maybe there's no direct way to do this, but maybe you can break it down into parts, and for each part maybe you can easily compute your beliefs. Maybe for each part you can compute your beliefs. So then you can use this total probability law to get a computation, get a handle on the event of your interest. Okay. So let me get to Bayes' rule. Which is actually just, I guess, a restatement of, I guess, conditional probability statement. And it has a couple of interpretations. So what is Bayes' rule? So Bayes' rule is this. It's the probability of event A given B is equal to probability of event B given A times probability of A divided by probability of B. Okay. So of course, this is actually, if you think of if you have, I mean, since from the previous a couple of pages ago, you know that probability of A intersection B is probability of A times probability of B given A. It is also equal to probability of B times probability of A given B. So, I mean, I just took the denominator in the definition of conditional probability to the right hand side, and um, and I get these two equalities, and I can equate now these two together, and I'll get this Bayes rule. But what is its interpretation? What is its interpretation? So you can think of B as evidence, okay, or a special type of event actually, and what you I mean, the way you interpret this equation is, let's say you have a belief about event A. Okay, so that's P of B. So P of A. Now B is another event, and maybe it has actually happened in the sense, for example, you're tossing coins. Maybe you did see a bunch of heads. Okay, now that can be considered as evidence, and now we want to update our belief. So this conditional probability plays the role of, is interpreted as an updated belief about event A, given that I've observed a bunch of heads, or given that I've seen this evidence event. Okay, so this updated belief is related to my previous belief. So this is the updated belief, this is the previous belief, and these two are related by a factor. Okay, and this relation between the previous belief and updated belief is evidence, is captured by Bayes rule. Okay, for example, let me give an example. Let's say I toss a coin, and um, let's say I toss a coin 3 times. Okay, so toss a coin 3 times. Okay, and then I observe that I have heads. Okay, so I toss the coin 3 times. I didn't log every time exactly what happened, but I have this summary information that, okay, I have heads, which means that the other two tosses were tails. Okay, I know that there was one heads. Now I want to find, let's say for me, the event A is that the first toss led to heads. Okay, and event B is one of the 3 tosses is heads, and we know that this has happened. Okay, we observed it. So we can ask, what is the probability of A given B has happened? This is just the probability of B given A has happened times probability of A divided by probability of B. Okay, so now let's just understand the numerator. So probability of B given A is that, so let's say A is the probability that heads happens, right? So let's actually tackle the simpler one. The probability of A, okay? Probability that the first toss is heads. Let's assume that the coin has some bias with which I'm flipping the coin. Let's say that bias is P. For example, P can be 1/2. So let's say probability of A is P. Then probability of B, that is exactly 1 heads in 3 tosses, given that A has occurred. That's what this conditional property means, is equal to not having heads in the next 2 tosses, which means that I have 1 minus P in the next toss and 1 minus P in the next toss. Okay. This is the probability of B given A has happened. Okay. Now, what is probability of B itself? That one head has happened in 3 tosses, is that it could have happened in the first toss, that is P, and 2 tails in the next 2 tosses, or it could have happened this way: first toss was a tail, next toss was a head, and next toss was a tail. And these are the beliefs, these are the probabilities with which it will happen. Or the first 2 tosses were tails, and the last toss was heads. Okay, so given this information, I can have my updated belief of that the first toss was a head, given that there was 1 head in 3 tosses, is equal to 1 minus P square times P divided by 3 times P times 1 minus P square, which is 1/3. So given that there was one head in 3 tosses, the probability that it happened in the first time in the first toss is 1/3. It's kind of intuitive, but it just works out because of the application of math. I mean, just working out the definitions here. So, so why is Bayes rule and conditional probability useful? It's useful. So what's the connection to machine learning? So there's actually the whole field of there's a whole field of machine learning, uh, which with a tool called graphical models, which includes Bayes networks and Markov networks. So and it has relations to what are called hidden Markov models and so on. So there we do use, for example, the um, multiplication rule, and so on. So that's the connection. So if you really want to understand Markov models, Kalman filters, conditional random fields, then it's good to understand conditional probability and Bayes rule, and also things we will see in the subsequent videos. That's all for this video. Bye-bye.